Hello class and welcome to our next lesson on section 4.5, periodic and piecewise continuous input functions. So theorem 1, we have if the Laplace transform of f of t exists for some s greater than c, then the Laplace transform of u of t minus a times f of t minus a would be equal to e to the negative as times capital F of s, and the inverse Laplace transform of e to the negative as times capital F of s is u of t minus a times f of t minus a. This is for values of s greater than c plus a. And that u of t minus a times f of t minus a is a version of that unit step function where it's 0 if t is less than a and f of t minus a if t is greater than or equal to a. So for example, we want to apply theorem 1 to f of t is equal to 1/2 t squared, and we have the graph there in the upper right that depicts this as well. But based on this theorem 1, the inverse Laplace transform of this would be e to the negative as divided by s cubed. This would be u of t minus a times 1/2 times t minus a squared. So this gives us, based on that last slide, 0 if t is less than a, and 1/2 times t minus a squared if t is greater than or equal to a. For example number 2, we want to find that Laplace transform of g of t if g of t is 0 when t is less than 3 and t squared when t is greater than or equal to 3. And we could see that going on here where we have our function g of t given by the solid lines, well, curves I should say, on this graph. So for this, we are going to write g of t as u of t minus 3, since 3 would be a in this case, times f of t minus 3. So this would be that we want a function f of t whose translation of 3 units to the right agrees for t being greater than or equal to 3. And we could see that going on in this graph on here, where that function here, t squared, connects this portion onto here. But in order for us to have it be agreeing to this, that is going to be, so this is going to be f of t would be equal to t plus 3, the whole quantity squared, in order for it to actually give us what we want on this graph. So f of t is equal to t plus 3 squared, then capital F of s, based on that Laplace transform. This is the Laplace transform this would be t squared plus 6t plus 9 once we multiply out this binomial squared for f of t. Okay, so by doing that, we are going to apply theorem 1 again. And that Laplace transform of u of t minus 3 times f of t minus 3 is going to be e to the negative 3s times f of s. So right now, this would be e to the negative 3s times 2 divided by s cubed plus 6 divided by s squared plus 9 divided by s. For example number 3, we want to find the Laplace transform of f of t, where f of t is cosine of 2t when t is between 0 and 2 pi, including 0 but not 2 pi, and 0 if t is greater than 2 pi. So we could see that break in our graph here in the upper right hand corner. So, f of t is equal to, this will be 1 minus u of t minus 2 pi times the cosine of 2t. And that's going to be equal to cosine of 2t minus u of t minus 2 pi times the cosine of 2 times t minus 2 pi. And this is because, or I should say due to the periodicity of the cosine function. Cosine function. So what does that mean for us? That means now we could apply theorem 1 again. And this Laplace transform of f of t is the Laplace transform of, this would be the cosine of 2t and that'll be the cosine of 2t minus e to the negative 2 pi s times the Laplace transform of the cosine of 2 pi. So this whole thing simplifies to just be s times 1 minus e to the negative 2 pi s all divided by s squared plus 4. For example number 4, we have a mass that weighs 32 pounds, or 1 slug. Is attached to the free end of a long, light spring that is stretched 1 foot by a force of 4 pounds, where K would be 4 pounds per feet. The mass is initially at rest in its equilibrium position, beginning at time t being 0 seconds. An external force, f of t is equal to the cosine of 2t, is applied to this mass, but at time t is equal to 2 pi, the force is turned off, so abruptly disconnected, and the mass is allowed to continue its motion unimpeded. We want the resulting position function x of t of this mass. So the initial value problem for this would be x double prime plus 4x is equal to a function f of t, where x of 0 and x prime of 0 are both 0. And f of t, which we were given on here as that cosine of 2t, is that same function we just had on that last slide of example 3. So, per example 3, the transformed equation that we get for this would be s squared plus 4 times capital X of s. And that would just be capital F of s is equal to, this would be s times 1 minus e to the negative 2 pi s, all divided by s squared plus 4. Alright, so x of s would be s divided by s squared plus 4 squared minus e to the negative 2 pi s times s divided by s squared plus 4 squared. So, from what we did back in section 4.3, the inverse Laplace transform of s divided by s squared plus 4 squared is 1/4 times t times the sine of 2t. Okay, so from theorem 1, our function x of t, this would be 1/4 times t times the sine of 2t minus u of t minus 2 pi times 1/4 times t minus 2 pi times the sine of 2 times t minus 2 pi. So that would give us 1/4 times t minus u of t minus 2 pi times t minus 2 pi and that whole thing would be times sine of 2t. So for this position function, x of t. We could separate this into cases. This is going to be 1/4 times t times the sine of 2t. This is where t is less than 2 pi. And then the other case is 1/2 times pi times the sine of 2t, excuse me. And this is where t is greater than or equal to 2 pi. Example number 5, I have considered the RLC circuit shown in the picture below, with R, a resistor, being 110 ohms, L being 1 Henry, and C would be 0.001 farads, and a battery supplying E sub 0 of being 90 volts. Initially, there was no current in this circuit and no charge in the capacitor, but at time t is equal to 0, the switch is closed and left closed for 1 second. And at time t is equal to 1, it is opened and left open thereafterwards, resulting in, and we want to find the resulting current then in this circuit. So, we know from section 2.7, and I'll write this one up here since this is technically not the answer just yet. 2.7, the equation that this uses is L times the first derivative of I with respect to t plus R times I plus 1 over C times Q is equal to some function E of t. Okay, so in this particular case, we would have, and I'll write it up here. In this particular case, we are going to have the first derivative of I with respect to t is equal, first derivative of I with respect to t plus 110 times I plus 1000 Q would be equal to some function E of t. But E of t, though, we know has that 90 volts. So this would be equal to 90 times 1 minus U of t minus 1. Why is that? That's due to the opening and closing of that switch. So from this, we can see that E prime of t, it has infinite discontinuity. Infinite discontinuity at t is equal to 10. So, because of this, we are going to use as our initial value, so I'll put initial value Q of 0 to be 0. So, from this, we know that I is the same thing as the derivative of Q, first derivative of Q, with respect to t. We want to then apply the use of integration, where Q of t is the integral from 0 to t of I of tau, d tau. So this then becomes L times the first derivative of I with respect to t plus R times I plus 1 over c. And I should probably make my I capital there so it doesn't look different. Plus 1 over c times the integral from 0 to t of I of tau d tau. And that is equal to our function e of t. So equal to 90 times 1 minus u of t minus 1. Okay. So, because of this, this can give us the first derivative of I with respect to t plus 110 times I plus 1,000 times the integral from 0 to t of I of t, tau, d tau, would be equal again to that 90 times 1 minus u of t minus 1. So, from section 4.2 that we've done, the Laplace transform of the integral from 0 to t of I of tau d tau is I of s divided by s. So, because of that, we can then give, as our transformed equation, s times I of s plus 110 times I of s plus 1,000 times I of s over s it's going to be equal to 90 divided by s times 1 minus e to the negative s. Okay. So from all of that, we could solve this. Right? So I of s would be 90 times 1 minus e to the negative s divided by s squared plus 110s plus 1,000. Okay. So, because of this, we could use those partial fractions to get that 90 divided by s squared plus 110s plus 1,000. This would give us, once we solve the partial fractions, when factoring that denominator, this would be 1 over s plus 10 minus 1 over s plus 100. Okay. So just so we have more room for this, and to continue then with the rest of that, let me just get rid of up here. So we could see what's going on with now this function. Okay. So, to continue then from that, I of s would be 1 over s plus 10 minus 1 over s plus 100 minus e to the negative s times 1 over s plus 10 minus 1 over s plus 100. Alright. So now if we were to apply the theorem 1 with f of t being e to the negative 10t minus e to the negative 100t. Alright, so now doing that, then, we could get the inverse transform to be the following. I'll write this as I of t. This would be e to the negative 10t, minus e to the negative 100t minus u of t minus 1 times e to the negative 10 times t minus 1 minus e to the negative 1000 times t minus 1. Alright, so our position function then can be written in our two cases. I of t. And this would be e to the negative 10t minus e to the negative 100t. And this is where t is less than 1. Okay. And then the other one is e to the negative 10t minus e to the negative 10 times t minus 1 minus e to the negative 100t plus e to the negative 100 times t minus 1. And this is if t was greater than or equal to 1. And there's actually one too many zeros here. There's only supposed to be a negative 100 here, not 1,000 in that exponent. But this then would then describe that position function with regards to this current. So the transforms of a periodic function, this is the non-constant function f of t is defined for t greater than or equal to 0, is periodic if there is a number p greater than 0, such that f of t plus p is equal to f of t for all t greater than or equal to 0, and the least positive value of p, if any, is the period of f. And theorem 2 gives us the transforms of these periodic functions. Let f of t be periodic with period p and piecewise continuous for t greater than or equal to 0. Then the transform, capital F of s, is equal to the Laplace transform of f of t exists for s greater than 0 and is given by capital F of s is equal to 1 over 1 minus e to the negative ps times the integral from 0 to p of e to the negative st times f of t dt. So this example 6, we want to consider a mass spring dashpot system. M is 1, C is 4, K is 20 in appropriate units, and we want to suppose this system is initially at rest at equilibrium, x of 0 is equal to x prime of 0, both being 0, and the mass is acted on beginning at time t is equal to 0 by the external force f of t, whose graph is shown on the bottom left. We want to the square wave with amplitude 20 and period 2 pi, which is what that's attempting to show. And we want a position function f of t, which you can see that graph on the bottom right. So for us to do this, we want our function f of t to be -1 to the power of the step function of t divided by a. Okay, so this is that square wave function. Which is what that's trying to describe on that bottom left. And the period p is equal to 2a. So, excuse me, this is not the step function. This would be the greatest integer function. So, that's -1 to the greatest integer function involving that t divided by a, not exceeding that t divided by a. So by theorem 2 that we just saw, the Laplace transform, and will be this capital F of s, is 1 over 1 minus e to the negative 2as times the integral from 0 to 2a times e to the negative st times f of t dt. So this can be written as, and I'll do it down here for maximum room. This is 1 over 1 minus, that was not minus, 1 minus e to the negative 2as times the integral from 0 to a of e to the negative st dt plus from a to 2a of -1 times e to the negative st dt. That's by breaking it apart by using that value of a to break apart that integration a bit. So this is going to give us, this will be 1 over 1 minus e to the negative 2as times, this would be, so we have those two integrations. Let me break these apart. Negative 1 over s times e to the negative st, evaluate between 0 and a, minus negative 1 over s times e to the negative st, evaluate between, this would be from a to 2a. Okay, so that will give us, and I'll continue that down here, 1 minus e to the negative as, the whole quantity squared, divided by s times 1 minus e to the negative 2as. And that would give us 1 minus e to the negative as divided by s times 1 plus e to the negative as. So because of that, this f of s, capital F of s, again being what we just wrote, 1 minus e to the negative as divided by s times 1 plus e to the negative as. We could write that as e to the as over 2 minus e to the negative as over 2 divided by s times e to the as divided by 2 plus e to the negative as divided by 2. And that can be written as the hyperbolic sine function, tangent function. 1 divided by s times the hyperbolic tangent function of as over 2. Let me know if you have any questions or concerns. Thank you.